All right, we have finished exam 2. I haven't gone in and updated the last minute grades on it though, so there still could be some more points that will be added to exam 2 depending on how Canvas decided to grade things. So that is not totally finished, but you've mostly all taken exam 2 and you know most of your grade. So there is one exam left. Let's look at the schedule just to kind of get an idea of what is left in the quarter. So this is the last little bit. There's 2.5 weeks, something like that. We're right here currently, class 23. So we're going to talk mainly today, just overview what's left and the trust project. So this will be a short one. At least I think it'll be a short one. I guess if there's any particular questions that show up in the chat, we can look at those. But I don't anticipate many. Maybe projects about the or questions about the project. So so we got the trust project. We'll talk about that. We've got this topic of torsion, so we'll spend the rest of this week and part of next time talking about torsion. Remember, the whole class is kind of divided into the first chunk of it is axial forces and stresses and strains. And then the part we just finished, which was pretty long, is the flexural stuff. So the beams and bending, shear and bending diagrams, moments of inertia were in there. Frames of machines were in there because they have beams in them. So that was a big chunk. And then the last part is torsion and related stuff. So, or maybe not even related stuff, just other topics. So we kind of divided the three types of stresses that you might encounter: axial, flexural, and torsion. This course does not combine them all together. If you're in a major like civil or mechanical, you'll take a follow-on course where you combine, now an object is stretching, flexing, and twisting all at one time, and you got to figure out what's going on. But in this course, we keep them all separate. So we're about to enter into the torsion section. There's another quiz in there, just like the other four. Don't forget to do quiz 4. I think it might still be open. So it did get kind of passed by because it kind of closed-ish during the exam, and I reopened it. So don't forget quiz 4. I'm not sure if people have done it or not. There are thin-walled pressure vessels, so things like airplane fuselage or a rocket fuel tank or a Coke can, something where the wall thickness of the container is pretty thin and there's generally a high internal pressure. Basketball is probably like right on the outer limit of being thin wall. With the ratio of the wall thickness to the diameter of the ball. It's probably pretty close to, maybe you're in thick wall territory at that point. I'm not sure. But we could find out. Stress concentration factors. So all of the calculations that we've done have kind of assumed that we're doing this average stress calculation. And that's fine, and it's actually where you start. But when you apply a load, like thinking about, we've been applying these point loads. Theoretically, this point load is applied at some point, but really it's spread out over a little bit of an area. We've had distributed loads that were distributed over a larger area. We had bearing stresses that were spread out over an area. But none of this stuff is like evenly distributed. You're evenly spread out. So the point where you apply that point load has higher stresses than anywhere else. Or if you drill a hole in a plate and then try to apply a force to it and then cause it to stress, then the stresses are going to be higher around that hole. And so the stress concentration factors are a way to deal with that without using simulation, without using finite element analysis or one of those processes. So this is pen and paper type of way of dealing with the fact that, well, yes, you can calculate an average stress, but there might be a piece of that object that you're working on that has a higher stress, and we might need to know that. And then class 29, so that'll be August 12th. You don't have to do this at all. You could just take a day off, at least from this course. And you can take exam 1 or exam 2 and redo them. Now, it won't be the exact same exam. So if like the same problems, all that, it won't be, there might be some overlap between them, but it will not be like a copy of exam 1 with different numbers in it or something. It'll be different exam one. It'll say the same content though. And what will happen is whatever you make on the redo, it replaces the old grade. Most everybody, like there have been a few who didn't, but most everybody improves 7 to 10 points. Occasionally somebody does make worse than they made originally, and they do get the worst grade, but usually it's worse by a point or something like that. You do have to choose if you want exam 1 or exam 2, so you have to pick that. And then it'll work the same way that we've been doing exams. You can take exam 1 and 2, or 1 or 2 at noon, or you can come at 7 and do exam 1 or exam 2. And then class 30 is exam 3, so you do need to take that one regardless. That one is a comprehensive exam, so it will go all the way back to resultants and cover all the little topics, including the new stuff: torsion, stress concentration factors, thin-walled pressure vessels. They'll be on there also. They probably account for, I don't know, 40-ish% of exam 3, maybe if I'm guessing. And then that's the last class, and so the last 2 things you do are just Zoom exams. So there's not a lot of new content left. Typically, exam 3 is the highest grade, of the 3 that you take. The new stuff is actually pretty simple, pretty straightforward. It's just a matter of learning it, but it's not complicated. And then exam 3 also covers stuff that you've already done, and hopefully you know how to do. The last day to turn in the report's actually August 15th. That's what we're going to talk about today, is this report. It's normally what we do. If we were in person, you'd get in a group of 3 or maybe 4 people, and I'd give you an assignment to build the strongest or strongest compared to its weight, so the ratio of strength to weight truss that can support a load in this location. And you'd design it in SolidWorks, you'd laser cut it, build it, actually go take it to the machine, and you'd predict how it's going to fail. Then we test it and see what happened. Most of that we can't do because we're not on campus. So what we do instead is similar to Lab 1 and 2, that Lab 1 and 2, you've been doing SolidWorks. And the project will also include a SolidWorks simulation, because you can't actually build and test this truss that you've designed. So let's look at the rules, the guidelines for what this project is going to be. I have them here. It does Truss Project Summer 2024 details. Now when you click on it, it does say 2023. That's just because it's the same as it was last year. So here are the rules, or the guidelines. You can have 3 or 4 people in your group. 2 is not ideal. 1 is not even a group. 5, there's definitely going to be some people not doing anything. So 3 or 4 people, 3 being the ideal number, but 4 is okay too. These people don't have to be located wherever you're located. You can work with them just like we've been doing, where you meet in Zoom or email, or half of you are in person and half of you are somewhere else, and however you want to do it. You don't have to be co-located in order to be on a group for this project. So the objective is you're going to design. So design meaning SolidWorks design, but also pen and paper design, like sketch out the truss members. These are trusses that we're going to do, so this is stuff from exam 1. You're going to analyze, so you're going to do the calculations, the method of joints, method of sections. You're going to figure out which of these pieces in your truss is the most likely to fail piece. You'll have to know something about the material. Now, we're not physically building these, so you get to choose a material and you get to look up its properties. I would suggest a metal material, just because the properties will be isomorphic then. In the course, in-person course, we use a engineered hardwood type of material, like a panel. And so that's kind of okay. It's laser cuttable and it's sort of isomorphic, But I wouldn't, wood itself, like lumber, is not isomorphic. It doesn't have the same properties in every direction, and so it gets hard to predict with it. Could you do home? Oh, there's a question. Well, yeah. We'll look at the web work. There's a question on a web work problem. We'll do that one at some point. So you got to be able to analyze this thing, and you're going to simulate. So I put using SolidWorks. Hopefully, in your group, I would make sure that in your group you have at least one person who has a working knowledge and version of SolidWorks, because otherwise then you've got to figure out, well, what are you going to simulate it with, and you might have some issues with that. Fusion 360 will simulate these things, but you may not have done that before, and so you've got a lot of new learning to do. I will go through SolidWorks probably, I don't know if it'll be soon. Not immediately, but maybe later this week or early next week, I'll go through and show you how to do a simulation of a truss in SolidWorks, just so you for sure know how to do that, because some of you may not have done that in SolidWorks either. But it doesn't have to be any particular truss. So this isn't going to be a competition like it normally would be, where everybody gets the exact same design criteria, and then they go and design and build and fabricate this truss, and we go test it in the machine. You get to choose what the goal of your truss is. So it might be a little bridge. It might be a lighting rig, like in a stadium where you've got all the trusses holding lights everywhere. Maybe a bike frame. Some of those look like trusses. It does have to be a truss, not a frame by definition. So even if it's something that's technically a frame, you have to treat it like a truss. So the members have two joints, no forces applied on the members themselves, and all the truss assumptions. We ignore the weight of the member, or if we don't ignore the weight, we split that weight up and put it at either end of the member. All of those things. It does need to be a truss that is, I've written it here, statically. Oh wait, well, I wrote it should not be statically indeterminate. So it should be statically determinate, but not statically indeterminate. And we'll talk a little bit more about what that means, but if you don't remember, basically you could have a truss, so it meets all the qualifications as far as joints and members and all that kind of stuff, but it is statically indeterminate. You can't use statics, the stuff we've been studying, can't use that to figure out the member forces, because usually it's because you've got too many members connected to one joint. So that, since you're creating the truss, it's entirely possible that you would just put too many members at one joint, and then you couldn't analyze it using our statics, method of joints, method of section stuff. So it does have to be one that you could use our methods, method of joints or method of sections, or both, and figure out all the member forces. So what you're going to turn in is a written report. This is like 10 pages, probably somewhere in that page length. Here's the format for the thing, and then I've got down here a little rubric. It's kind of small, probably on your screen it's really small unless you're looking at a large screen here, but look at this, download this, print it out, whatever. This is the rubric of how I'm going to grade the report, so make sure you understand what I want you to put in the report. It does not need to be a terribly lengthy, like 100-page report or anything. I think you can get all of this in 10 pages. Maybe you have 10 pages plus the title page, I don't know. But it's not going to be a terribly long thing. Make sure that every student's name who's on the team, or who wants to get credit for that, make sure they're on the title page, because that's how I'll award credit. Only one person per team needs to upload the report. You don't have to each upload one. Just make sure everybody's name is on that one that you do upload. So all of these are in this thing called Trust Project Summer 2024. When you look at it on the front page here, details. So this little link right here is the one that has that PDF with all the instructions in it. And there aren't that many instructions. Basically, you pick a team of 3 or 4 people. You design and analyze using, some of it you do by hand, but you also simulate it in a program like SolidWorks. And then you discuss your results. So make sure you read through what I want in the report format, because that'll give you all the little things you need to do. Okay. So far, the only question I see is about a web work, so that's not. We'll get to that one once we are done with this project stuff. But if there are project questions, put them in the chat so I can answer them while we're looking at them. These two links, MD Solids, and let me make sure the buckling still works. Sometimes they take these down. Let's see. Nope, that one still works. All right. So these two links are links that you might find useful for verifying your trust calculations. So MD Solids, click on here, open it in a new window so it goes to a new page. It is a piece of software, so this is it's an old piece of software, mind you, and I assume it still works. I actually have not tested it on Windows 11. When is Lab 2 due? Lab 2 was the one with the 3-point bin test. We just went over that. Let me see when it actually, because sometimes Canvas carries over dates from previous years and they are not right. So Lab 2, let's see, Lab 2 report, it says it's due like a year ago, so that's not true. Let's change that to, where's the, I think maybe in here. Let's do the due date to be, today's the 29th. Let's get in 2024. So, whoops. I don't remember what I said. Let's put the 5th, I think the 15th is the last day to turn the the project. Let's do it the 8th is the last day for Lab 2. So August 8th is what I have now. Now it has, hopefully, the right due date on Lab 2. All right. So let's download this. I don't know if this computer ever has had it. Okay. Not sure why it won't let me download it. I wonder if it won't download anymore. I may have to try, like it doesn't actually want to download. I wonder, so one of the things about this piece of software is it's kind of in its last state of whatever situation it was in. It used to be up in that state. They even gave you the registration code, but currently doesn't look like it's letting me download, but it says check internet connection, but I don't know. I mean, I'm streaming, so I think my internet's fine. So there might be, maybe we can't download this. I will look and see if I have a installer version still on an older computer somewhere. Maybe I do, maybe I don't. I don't know. I used to have one in an email. I mean, this is 2013 when this was out, so it's been a while. But if it won't download for us, then there's no sense in me telling you what to do with it. But what it was, or maybe still is a piece of software that allows you to do a lot of things, calculations related to statics and strength of materials. And one of them was it would calculate, you could literally draw a 2D truss and it would calculate the member forces. I think there are other online tools that will do that also now. At the time, 2013, there weren't that many options, but maybe there are some new options for doing that. It also would do some of these other things, calculate moments of inertia. It would draw shear and bending diagrams, all sorts of things. Maybe it won't do those anymore. I don't know. I'll dig around and see if I can find that. If it does, if I can find it, it's a pretty nice little piece of software that will help you quickly draw up a truss and see if it's the one you want to do. It doesn't do the stresses in the truss, but it'll do the member forces in all of the members, and so you can figure out if you've got a decently designed truss for what you're trying to do. But right now it looks like it's having some troubles here, so I might have to go and see if I can find a installer that I have somewhere, because it definitely doesn't look like it wants to let me download it right now. All right. The other piece of software that was shown on that page was a online. It was just online column buckling. It was this one. Because in the truss, we only really thought about the member forces and the stresses in there. But any of the pieces that are in compression, a truss member is generally a very long compared to its width, so it has a high aspect ratio. And pieces like that are in compression tend to want to buckle. And so you have to consider buckling as an option for the mode of failure. Now we're going to try and simulate this in SolidWorks, but sometimes SolidWorks, I don't know, doesn't do buckling quite the way I want it to, and so you have to manually go in and calculate buckling. Anyway, we'll get to that at some point. All right. Homework 17, problem 4, D through F. So that sounds like a lot. Let's look and see what that is about. Problem 4. Oh, it's another one of the beam deflection ones. So we are finished with beam deflection as far as exam 2 because we've taken exam 2, but it is possible that exam 3 would have a beam deflection equation on it or a problem on it. So this one, I think we've actually done part. Well, I didn't put the answers in here, but I think we did part of this one maybe. Maybe not. We'll look back in our notes here and see if we have that one anywhere. Let's see. So that one has a simply supported beam with a cantilever section. Let's see if we've done that. No, not that one. No, nope. It looks familiar, but maybe we never did that one. It'd be nice if we had a start on it so that that's similar, but not it. Maybe we didn't. That's almost it, but not it. And that's the first beam deflection. So I guess we didn't. All right, so we'll start from the beginning. We might have to do parts A and B in order to do parts D, E, and F, but we'll see. We don't need that part. Oh, we did homework 17 question 5 and 2. Okay. So we never worked on this one. All right. So let's see. We've got a simply supported beam, so a pin and a roller. It does have a cantilever section, and it has a point load that A and B is offset, so it's not centered. And we have an evenly distributed load across the whole simply supported section of the beam. All right. And it's a W8 by 31, so we have a beam that we can look up I. We don't have to go calculate that. And then we are neglecting self-weight, so we don't have to worry about how much the beam weighs. All right. So part A is the deflection midway between the supports. That's pretty straightforward, and it's not even what's being asked. It's being D and F. I don't think solving point A will help us with D through F, so let's not do that. Slope of the beam at C. That one we actually do need because that will help us solve. Well, no, that just helps us solve problem C. The deflection at B. So I think we don't need A, B, or C to help with D, E, or F. Ooh, the location on the beam of maximum downward deflection, okay. And the maximum downward deflection of the beam. Okay. All right, so yeah, I don't think we need to do A, B, or C, if I'm thinking about it correctly, but we'll find out. All right. The deflection of the beam at point B. Let's do that. So one thing, since we're neglecting self-weight, as long as we're neglecting self-weight, then this part of the beam, CD, is not affecting the deflection or anything between A and C. Now, if CD weighed something, like if we did not get to ignore the weight of the CD portion of the beam or any part of the beam, then yes, that part of the beam, the cantilever overhang part, would be trying to bend the beam between A and C, but we're told to neglect that, so we really don't even need that piece of the beam for parts D, E, and F anyway. So that's useful. Let's draw. We're gonna have to do superposition, so let's just do side by side beams here. So this is going to be my pin on this end, and I'll have the roller on the other end. Make it a round roller. And I'm going to ignore the cantilever because it's not doing anything as far as what I'm interested in for this particular part of the problem. So I've drawn two of them here. I've drawn two so that I have the point load on one of them and the distributed load on the other one. So let's put the point load on the left one. The point load is a distance A, so that's the smaller distance. And A is 3.7 feet in my problem. And B 6.9. Oh, wow. I thought the touch... Oh, hold on. Gotta reset the screen because if the touch is not off, then it gets really hard to control. Let's see. Every now and then it needs a reset so I can turn the touch feature off. There we go. All right, now when I touch the screen, it doesn't actually go crazy. All right, that's pretty much it for the point load. The distributed load's even more simple. It's just across the whole thing. I guess I have values for these I need to put in there. For the point load, it's 1,047 pounds. The distributed load, 76 pounds per foot. And this distance is, well, it's the sum of those other two. Well, we covered over our 76. It's okay. So that's what? 11.6. I gotta find my calculator. Oh, 10.6. 10.6. Now, before we do too much, we need to figure out some stuff about the beam. It's a W8 by 31, so we need to go get our beam properties. W8 makes it sound like it's an inch series beam, so that's a little bit easier for us because I actually have the inch series W here. Well, here. And we need the W8 row. Well, there's several rows. Let's get those. Let's put put that up here. There we go. It's W8 by 31, so that gives us that row. Doesn't want to, well, sort of like that. I think it's the 110 number, but let me go back over here and make sure that that's the right column. Yeah, 110 inches to the fourth. I don't know why. What is it doing? Just, wow. I don't know why it won't let me right there. All right, so that's the moment of inertia. Oh, somehow I pasted one of them down there. Okay. Now we need our beam deflection equations. So I think we're done with this. I don't think we need it for anything else. I think the clearest set was in here. Nope. In the second one. Yeah. Now, you know, this chart isn't from the book that the WebWork problems were created from, but I think the equations should be the same. Like, they might look different as far as the way they're arranged, but I think they should be the same. All right, so we have case 7 here. Simply supported beam with an offset, not centered, point load. And we have case 8. So we are trying to find, you said D. Yes, D through F. So we're trying to find the deflection of the beam at point B. Point B appears to be directly under the point load. It doesn't actually say that in here unless it was something I didn't copy. But the way it's drawn makes me think point B is directly, like it's right under the point load on both beams. So, let's see for our offset point load what we have to choose from. So I wonder. Let's look at the ones that come with the book to see if they present it any differently. Oh, did the wrong button there. Those would be, I guess they're just in exam reference. But they're in exam reference 1, not 2. So they give us this. So they give us one equation from x equals 0 to a equal to a. So actually, let's use this one because the other set, I don't think it gave me one where it equals the point. So even though it's blurry, let's use this equation. Now in this equation, we have to make sure that we are checking that A in our diagram is the longer distance. So it's not the one on the left. It says over and over here, B is less than A. And it shows us a picture where B is the short distance, A is the long distance. So we definitely want to make sure that it's not a left-right thing. We're actually going and finding, when we plug in a value for A or B, B is the smaller number, A is the bigger number. Okay, so this says we should be calculating, and wow, I'm going to go ahead and open up MathCAD just because, that looks like it's going to be a lot easier than plugging this in on my calculator, but we'll try it this way. So it gives us a negative sign because it's pointing downwards, because that's a negative direction. So y from the point load equals negative p is the value of the force, times b, which is the smaller distance, 3.7. Now these are feet, right? Yeah, these are feet. So I do need to make sure that I'm dealing with my units if I'm doing this by hand. X here, X is weird. Let's go back to our picture. You can see the y-axis on the left-hand side of this beam. So the y-axis is actually measuring the longer distance. So this could be a place where you would get tripped up pretty easily. X in here is actually 6.9 feet. Okay, that's weird because of normally we're measuring X from the left going towards the right, but our diagram says to measure X, and it's going to start at the beginning of the longer distance and measure that way. So X is actually measuring from here this way. Over 6E. We haven't done E. Let's see. This is a structural steel. I happen to remember for the US units, structural steel is 29 million PSI. I is the number we looked up, 110 inches to the fourth, because it was a W8 by 31, I think. L is another one that could be tricky. L is the length of what's shown in your picture here. So it's only the distance between the pin and roller. So it's only the 10.6. That's kind of one reason I drew these as only simply supported beams, because for this question, the cantilever section isn't doing anything. So this is 10.6 feet. Now MathCAD will handle these units without any trouble, but if you're doing it by hand, I've got feet and inches all mixed together in here, so you do have to be careful with that. B is the shorter distance, that's the 3.7. Minus X is the weird one in this case. And yeah, we could do that with our calculator, but why don't we use this equation instead of max deflect? Oh, so yes, so there is a this version right here, PB L squared minus whatever over 9 square root of 3 is the maximum deflection, but if you look, this one even shows it. Let's zoom in a little. So, whoops, too much. So this one even shows it. The other one that we were looking at earlier chart doesn't show this, but the point load is not where the maximum deflection occurs when you have an offset point load. When you have a centered point load, the maximum deflection is right under the point load. But when you have an offset one, they're not lined up exactly. And this version, the one from your book, actually shows that the Y max is not underneath the point load. The other one that we were looking at that's clearer, you know, it's a nicer picture, doesn't actually show that, but it's something you're, I guess, have to know. This one gives you the equation here that here is the Y max equation, and it tells you it's at some weird, you know, you have to calculate where it is. And so if you calculate this, then you could just look at it and see, well, that should just be A, you know, at X equals A. but it's not. It's at some other point. Let's see if we can throw this in MathCAD and get some number. So we've found out that I is equal to 110 inches to the fourth. E is 29 times 10 to the sixth PSI. Oh, not bad. L is A plus B. And A is, all right, A is the longer one, so that's the 6.9 feet. B was the shorter one, not BB. B is 3.7 feet. And we've got Y is equal to negative P times B times X. Oh, X is also equal to A in this setup. E times I times L. That should be a capital E though. Need it to go on the other side. Times L squared minus B squared. Oh. Minus B squared minus X squared. Didn't really want that. There we go. Now, is this correct? PBX 6E I L L squared minus B squared minus X squared equals. Oh, the force. P is 1,047 pounds. Let's put it in inches. So it says negative 0.12. We probably need more decimals in there for WebWork to be happy. So there we go. That's one piece. That is the deflection underneath the point load at point B, which is what we're asking for in this problem. This is D. But it's only the deflection from the point load. We also need to do the distributed load. So let's see what equations we have available for this one. We've got, in this setup, it's number 6. Now, the slopes don't do us any good. Y max, that is not useful for us. We have just this equation of the elastic curve. So we need this entire equation. And here, since it's distributed, it's evenly distributed and it goes across our entire beam, minus the cantilever section that we're ignoring for now, for this part of the problem. Then X, doesn't matter which direction we measure X from. We'll just measure X from the left end side like we had set up to be. But let's put this equation in. So I'm going to copy it so I don't forget it. Oh, not there. Let's put it over here first. Let's move that over. Maybe we can make it a little smaller to make it. There we go. Okay. Now for this one, it's also negative because the way the distributed load is applied to the beam causes it to bend downwards. W is the value of the distributed load. It is pounds per foot, so if I'm doing it by hand, I got to deal with the feet to inches issue. Here, it seems weird, but we need to rethink where X measured from. So we're going to measure from here. Because in our point load is over here, and this is the point that we're interested in, point B. So that's the distance, that 3.7 feet. That's the distance I'm interested in. So that may be, hard to visualize why this is. Why? Well, this one's probably easy to visualize. The x being measured from the other direction is probably the hard one to memorize or make sense of. So in the chart, would x be equal to b length or always a length? In the chart, let's go back to the chart and make sure about that. In a chart like this one, case 5 up here with the offset point load, x in this equation, the equation of the elastic curve, it even says it's only good, well, this version of the chart says that x can only be from 0 to a. So this version of the chart only even gives us equations that we can plug in values from 0 to a. We can't even do the other little section, the short section of the beam. I think the other one, the clearer chart, gives you 2 different equations here. One for 0 to a, which is the longer length, and another for 0 to b, which is the, or well, from b to l, I guess, for the shorter length of the chart, beam. So it kind of depends, but with this one we're looking at right now, you can't even put in values that would calculate the deflection on the short side of the thing. And it tells you that x starts at 0 and it goes to a. And that's also how they show it in the picture here, because you can see the y-axis starting on the left-hand side. But for our setup, we had to put the y-axis on the right-hand side to match the fact that, not the fact that the y was on the left or the right or anything like that, but it was associated with the longer distance. You know, x equals 0 here, and x equals a 6.9 feet at point B. So, yes. So in the chart, would x be equal to b length or always a length? So actually, x doesn't have to be a. No, well, that's too many a's and b's. X does not have to always be defined to be the value a. Technically, x can be, you know, any point along the way here. It just can't be over here. I probably shouldn't make x's over there. So we actually wanted, the problem told us to find the deflection at point B. So in that case, x needed to go all the way to point B, which I know that's why is it labeled B if we have, this is A, whatever. But the point underneath the point load, and that happens to correspond to point A. But if we could have been asked for, oh, you need to find the deflection over here at point C, or, you know, some other point. And in that case, x would be, we'd still need to measure from the beginning of the longer section, the beginning of the A section. We would just only measure out that far, whatever that distance is. So it's not that it's always A, like the whole length of the longer section. It's just, it can't go past that. And you have to measure from the beginning of the long section. Hopefully that makes some sense. Let's see, we have W, X in this. So now forget all that. And the distributed load is a lot simpler. I should have started with it, I guess, now that I think about it. The distributed load is evenly distributed, so it doesn't, the mirror image of it is the exact same. It doesn't matter which way we look at it. So I need 3.7 feet here. Times E times I. Well, let's put the values in there. E is 29 million. PSI. I is 110 inches to the fourth. X cubed. In this case, X is going to be 3.7 feet cubed. Minus 2 times L is the length of the beam. Well, the length of the part of the beam that we're dealing with, so that's the 10.6. Times X, which is 3.7. and only the x part is squared, plus the 10.6 foot cubed, and we're about out of space there. Okay, let's see if we can get that into MathCAD and have some agreement here. Let's make this y point. Oh, what are you doing? Y. Oh, this is a different version of MathCAD. No. Don't remember how to do the subscript in this version. Let's just do this. All right, so it's negative. We need to put a value for W in here. So W for me was 76 pounds per foot. Okay. So W times X. Oh, well, we need to redefine X because we had X equal to A on that first part. In this one, X equals B. Over 24 times E times I times, whoops, all of that times X cubed minus 2 times L times X squared, all of that, plus L cubed. Okay. In inches, probably need more decimals. And the total y at point B is equal to these two added together. And let's round, or not round, let's expand. 1766. Okay. Let's see if that's what WebWork wanted. Got to get out of this thing. Where's WebWork? So that would be this point, negative 0 point, how many zeros? Just one. Let's see. Oh, gotta log in. And that's correct. So that one, it's not difficult. Well, yeah, doing this by hand probably is a little bit tedious because there's a lot of unit conversions you got to deal with, and you know, keeping track of these numbers because they're really tiny numbers, and so you probably can't round them very much, and WebWork still be happy with them. So by hand is probably very tedious. Assuming you don't have to worry about the unit conversions and the units, or not units, but the decimals, then it's not too bad. But it does take some thinking about what are you given in your picture. So, you know, in your set of equations here, what are you given, and how does that match what your problem statement actually has? So that, particularly with the offset point load, that's the one that probably has the most things you have to be careful about on it. This one is similar. The concentrated moment at one end, it does have different equations for the slope at both ends and stuff like that. So it's similar, but probably the offset point load is the most confusing of these. That's probably also why it's on one of these homework problems. Okay, let's see. So part E, the location on the beam relative to point A, so it tells us to measure from the left end basically, of maximum downward deflection. Okay. So that one's a little tricky. Let me look at what we have to work with here. So we have that one. That one's not too bad. That one. So here, maximum deflection is right in the middle. So that's not a big deal. Here, maximum deflection is near the middle, but it's not at the middle. It's got this weird point. But it's in the longer section. So it does show it in the section A. And we have further over here, if I zoom, I guess, that way, we do have an equation that gives us that. So this one by hand is probably not the one I want to do by hand. Because I think the only way to do this, now there might be another way that I'm not too certain about right now, but I think the only way to do this is I need to take both of these equations of the elastic curve, add them together, and then find their inflection point. So I think that probably means take both equations, get them set up to where, you know, like this one, the x is one thing, then the x is another and the other thing, so I have to deal with that. Take the derivative of that resulting equation, the two added together, set the derivative to equal to 0, and solve for where that is true, and that will be the point of maximum deflection. Might be able to get close enough just plotting them and trying to, you know, trace on MathCAD or something and find the point where they max out. Maybe that would get close enough. I suspect WebWork won't like that, but we could try that first. But I think that's what we have to do. So fortunately, we do have those equations built in here, but I didn't really set this x and this x are not the same in both of these. So I'm going to go back and hard code these in. So x for this one is supposed to be 6.9 feet. So I'm going to copy, well, just that equation. Oh, I didn't copy it. Oh, because I just need this part. Okay, and we're going to make x equal to the 6.9 feet in both of its instances. Everything else should be fine. Oh, but that didn't square correctly. Let me do that. There we go. Okay, now does it give me the same? Let me make sure it gives me the same number it did before. It does. All right, so that's fine. Whoops. We can probably need, yeah, we need those parentheses. Plus, so all of that, plus this guy. This one we can leave x at b because that's fine. All right, so if we need to make our window bigger because we ran off the screen. All right, so let's make sure that these add together to give us the, oh, no, oh, wait, that does need, oh, wow. I can't put 6.9 in there. Well, let me first make sure that this gives me the same thing it did before. It does. All right, so, but I can't put 6.9 in there because I want to solve for, I don't think that's the point where maximum deflection is, so this needs to stay x. The problem is, since I'm measuring from the other direction, wow, how do I just do L minus X? I gotta think for a second. Or is it okay for them? No, that's, yeah, wow. I need it to create, all right, so I need it to create that shape. So the beam, let's just work through this. The beam is going to bend something like that. There's our maximum deflection for this guy. This one is going to bend, you know, perfectly symmetric. Maximum deflection is going to be right in the middle. So when I add those two curves together, the maximum deflection is not going to be exactly in the middle, and it's not going to be exactly where the maximum deflection from the offset point load is. It's somewhere in their average, but I don't think you can just average them either. So my problem is, what do I put for x in the in this equation? Because this x is measured from a different direction. Although the other beam doesn't care. It can also measure, this equation also measures x from this way just as well because it's symmetric. So I think I can do x. But in my version of x, it will be actually measured from the right end of the beam. So the actual answer will be different. Okay, so I think we can do it. But these all just need to be x, and we need to understand, let's undo that. So let's make this a function of x. We just need to understand that this x that we're dealing with in this equation is measured from the right end of the beam. And I think it'll be okay. Okay. Oh, we also need this to be x. Now let's plot it just to see. Let's do a plot xy. And this will be y total of x. Oh, wait. There we go. And this will be x. Let's make it in inches. Why does it only give me 1 point? Oh, because I've got x defined up here. There. Why is it thinking that? Let's give it a specific range for x. X is going to be 0 to 0 point. Oh, let's put inches in there. 0 inches to 0 point. Let's do by 0.01 inches. And we've got to go out 90 inches. Well, what is it? It's 6.9 feet is what it has to go to. Okay. Now let's see if we can insert a plot and it work a little better. The y should be y total. I think I have to tell it it's a function of x. There we go. All right. So, again, this is the mirror image of what we look like in our problem statement. But here, somewhere around here is our inflection point. So I think if we, how do we trace this thing? Trace color? No, no, no. I thought there was a way to trace on here, but I don't see it. But we can see that it's somewhere 1 point, I don't know, 7 or 1.68 or something feet. Does that make, oh no, that's meters. Let's do feet for these. So it's at right about 5.6 feet, which seems about right. Seems in the right range. So I wonder, I need to take the derivative, I need to find the maximum of this equation, right? So I don't know if MathCAD will do this for me or not, but we'll see. Let's copy it. Oh, you know what? What might do it? Sometimes when MathCAD, I don't know how to do a particular thing in MathCAD, Wolfram Alpha sometimes will do it better. Although I don't have the paid version, so I don't know if it'll do this. Let's see. How would I ask it this? Or, well, 0 of that equation. Oh, no. Too many characters. So, Wolfram will not save us. Maybe if you have the paid version, then it'll do an unlimited number of characters on there. But so that won't help. Let's just try to see if we can do the derivative. Where's that at? Maybe we can just do a derivative. Did I ever copy it? I don't. Oh wait, maybe I need to do. How do I need to do this to get it to work? Can I do this? Probably have to do that. No, well, it actually literally not what I wanted to do. Just get rid of that section of homework. That's one way to do it. I don't know the best way to actually. Well, what I need is I need the derivative of this thing. Or well, that's a way to do it. Get the derivative, set it to 0, and that'll tell you the location where this is a horizontal slope. If I could just trace here, that would be close enough. I just don't know how to trace on this version of MathCAD. Maybe it's in the plot somewhere. I can add a trace, but that's not what I mean. Like I can't actually. Guess I could just do that. But I need a vertical window. I could get this guy to equal 0. Where's my plots? Add vertical marker. And then we'll see where, like 5 point, I don't know, somewhere in that range. 5.606. I'm almost certain WebWorks not going to be happy with that. It wants 5.012 or 013. Oh, that's actually way over here. So that's not what we have. It wants it way over there. So maybe I've got something in my equation not right. PBX 60L L squared minus B squared minus X squared in a weird way. WX 24EI. The equation looks right. I'm adding 2 negative numbers, so that looks okay. But, and so that should be the equation of the elastic curve, but it's showing that it maxes out way over here somewhere. Oh, right, because I have to measure. So mine shows 5.621 or whatever, but I'm measuring from over here, and the problem says relative to point A, which is over here. So I actually have to subtract the length L from whatever I'm calculating. So L is, well, 10.6 feet. So max delta, or max y, I guess, equals L minus the thing that I'm calculating, which it looks like it's 5.621 feet. And, you know, 4.979, it wanted a little bit different number, probably not enough tolerance. It wanted 5.012. So probably not the best way to do it. 4.9789. And it probably won't like that. Yeah, doesn't like that. It's not close enough in WebWork world. So what you really, the best way to do that is to take this process, but in order to find, you know, where is it actually zero, unless MathCAD has a thing that does that, which I don't know that it does. I don't know that it lets me do that particular thing. Also, I only have so many, you know, values in here based on what I put in here as my step size. So a better thing would be take this equation and find its, you know, derivative, set the derivative equal to 0, and see what the location is for that. That would be the more precise way to do it, because, you know, where are you going to say that this is exactly zeroed at? You know, it looks like somewhere in there. In this case, 06. And then I get a little bit closer. So, you know, you'd never, as far as WebWork, unless you just got lucky, since WebWork doesn't tell you if you're high or low or anything like that, unless you just got lucky, this would be a hard way to solve the problem in WebWork. It's completely fine. 4.994 is the same as 5.0 whatever, 5.01. So those are the same number in feet. You know, that's essentially the same thing. But WebWork wants you to be a lot more precise. The only way to do that would be to actually do the derivative and set it to 0. So, oh, I probably needed to do a symbolic version of this. Like, let's just give it one section, one chance to do that. Let's see. One of these is derivative, right? I thought there was. Maybe not. Maybe there's not. Maybe you can only do actual, like, closed stuff. I thought you could do a derivative, though, but unless it's in here, I just don't think it is. Anyway, that's how you would solve this one. Well, then once you get that, the next part is not that big a deal, right? So the next part is the maximum, the value of that. So now you know where the maximum deflection occurs. So what's that value? Once, all you do then is you take that number, plug it into your equation that you use to find that number. Well, not the derivative version, but this one. So 5.0. Let's just cut. Oh, come back. Get off of there. Can I? Feet. Can't copy that. Wow. And put that number in for x. Well, let's say yes, but x equals L minus that number. And then, oh, well, no, we have to do, hold up. We have to do this. No, not that. Y total, put that value in there. This is a problem that's definitely set up for a numerical solution of some type. And then here is the maximum deflection value, which, let's see if we got that part. Yeah, that looks like that same number. So that the last part is pretty straightforward. It's figuring out where is that maximum location, and it would be creating an equation that describes the whole deflection of the beam. So adding the two equations of elastic curves, getting their coordinate systems lined up so that you can add them, which in this case is doable because, well, because the distributed load doesn't really matter. This equation works the same whether you're coming from x equals 0 at the pin or x equals 0 at the roller. It's the same equation because it's symmetric. The loading is symmetric because it's evenly distributed across the whole thing. So we can add that equation to the one where we do have a difference in where x is measured from. We just have to remember that they're actually asking in the problem, they're actually asking to be measured from point A, which is the left end, which is not where we're measuring from. So it's a convoluted problem to deal with. And I just can't get MathCAD to take the derivative of this because I don't know exactly. I'm sure we could fumble around and figure it out. But for you guys, maybe you know how to get MathCAD to take the derivative, and it's probably not that big of a deal. It's probably relatively straightforward. I just don't know where in MathCAD to do that. If you can't get this and you can't get close enough with this method here, because you'd have to just kind of get lucky a little bit or spend a whole bunch of guessing to figure it out, then just send me an email and I will show you, I will give you your value for this number. But that's the process for doing it. It's just definitely not a test question. Definitely something you have to do long form on MathCAD. Wolfram, if you have enough characters. Maybe when I pasted this into Wolfram, it does paste it in like an Excel. And so it probably could be made a lot simpler if you just wrote it in manually. Hey, we have agreement on just get rid of that section. I think you can do it. It's just you might have to get some assistance from me on what is your value for x here, because it's tedious, or get this thing to take the derivative of it, which I don't remember. I know you can do it, I just don't remember how to do it. All right. So we did this more or less. At least we discovered the trickiness of this one, why it's such a not straightforward problem to work on, even though it doesn't look that complicated. It's got two loads on it, and you're ignoring the weight of the beam, and so it looks pretty straightforward, but it's quite tricky. Wednesday, we'll do some torsion. Start forming your teams. So that's one of the hardest parts. The hardest part, since you're not all together, is waiting too long and not getting a team together. So that creates a lot of problems. So make sure that everybody, now we're past the drop date, so everybody in the class still needs a team. And go ahead and start working on that. 3 or 4 people. If you absolutely can't get that to work, send me an email of why, and I'll see if there's a reason enough to grant you a team that's not 3 or 4 people. Yes, exam 1 retake and exam 2 retake, or you can't take both of them, so you just pick one, and they're both at the same time. So at noon, I'll give you whichever, I'll give you both access codes. Whichever one you start is the one you're taking, or at 7, whichever one you're doing. You can't do both though. You can't like go at noon and take exam 1 and go at 7 and take exam 2. You only get to redo one of them. Or the score lower? Yeah, nope. You keep the most recent one. The most recent one best describes your current knowledge of the material. So it's not the higher of the two, it's the most recent one. So the retake. I've only ever had like 2, maybe 3 people I can think of ever make lower, and when they made lower, it was a point lower. So it wasn't even that it changed that much. Most everybody, the vast majority make 7 to 10 points higher, and then some people make way higher because they did so bad on the first exam. They had a reason why the first version was really bad. That was a bad day or whatever, and then when they retake it, they do way better. But the average is 7 to 10 points better. But it is the retake replaces, no matter what the number, it replaces the previous attempt. All right. We'll be back Wednesday at noon. I don't see any more questions questions in the chat. So we'll be back Wednesday at noon, do some torsion. Go to Discord or wherever, or in person if you see people in person. Get your team set up. And will it be similar to the original? Oh no, it's the same difficulty. It's just slightly different problems. So it's not as simple. The retake. We're talking about the retake now. The retake is not as simple as you take the exact same test with different numbers. It's not quite that simple. But you did a resultant problem. You just do a different resultant problem. You did an axial stress problem. The retake has a different axial stress problem, but the same level of problem. It's a one-step problem or a two-step problem or whatever. But it's the same level across the questions, but they're not the exact same questions. Oh, C and E on 17.5. Maybe. The deflection at A. Yeah, so I think we actually did start this one. We didn't finish it. So I might have that one. Yeah, there it is right there, isn't it? Isn't it? Yeah, that's it. All right, so we did, I don't know, maybe part A and B or something. We did a bunch of it. So this was a couple of days ago, and you're asking about C and E. So C, the deflection of the beam at point A. So I drew this little curvy line here because different pieces of this beam are causing it, or different loads on this beam are causing it to deflect in weird ways. So the red distributed load here is causing the middle span to dip down, but it's causing the wings, to bend up like that. The, whoops, where'd it go? There we go. Sorry. The point load 8.9 is causing the beam to do something like that. Well, the blue distributed load is also causing the beam to do something like that. So you've got to take into account all three of these different effects. Point A is the point on the very far left end, I believe. Make sure. Yes, it's tiny, but yeah, there's point A. So what you have to do is the point load and the distributed load, how they affect point A are by making the pink section that I've drawn here, they make it slope somewhere. So I think that might even be one of the questions. Yeah, so part B here, the slope of the beam at point B, right here, that is the beginning of solving number or letter C. So if you know, let's say, I don't know how to draw this. Let's see. If you know that here's our pin and our roller, and I don't remember which way it's sloping. I've got a gray line drawn here that kind of gives it a positive slope. I don't know if that's true or not. But if you know that overall, between the point load, the red distributed load, and the blue distributed load, that the beam is doing, something like that, and you know that the slope at the pin is some angle, theta. If you know that, which you do if you were able to solve for number or letter B. So assuming you know that, then what you do is you say, okay, then if this is the right slope, then I'm going to start out with that little piece of the cantilever, kind of like this, and then I'm going to put my distributed load on it. Well, I colored it blue, didn't I? I'm going to put my distributed load on there, and I'm going to say that that distributed load continues, you know, to create some kind of deflection in this little cantilever section, and the total deflection is there's my axis, I suppose, is the amount that it's sloped here. So that would be you know, I've got a lot of stuff going on here. Theta times it looks like 1.95 meters would be, actually I shouldn't write it that way, hold up. This distance is theta times 1.95 meters. It's just an arc length. Basically, it's the fact that the beam is sloped down some amount, or maybe it's sloped up, I don't know, but it's sloped down some amount, and then the point, or the distributed load across here is going to keep this thing deflecting more, so I have to add on this. So this is going to be the delta from the distributed, or the blue distributed load, the way I've got it set up. And I add those two things, theta from theta at B times the length of the blue section, plus the delta of the blue section, which is case 2, I think, in your chart. It's just the cantilever with a simply supported beam on it. Add those together. That should be the total deflection for point A. So it's a lot going on. Would you not just do arc length? The arc length is a piece of it, which we just, but didn't we already take into account the blue distributed load to find theta B? Yes. But we did that to find the slope. So we did that to find basically this gray line that I've drawn with theta on it. And the distributed load, not just, like, it doesn't just cause it to rotate, which is what we were doing in the first case. It causes that little blue section to bend. So it rotates, and what we're imagining is that that little section is tilted down at some angle that we've already calculated, and then the distributed load continues to push it down to cause it to flex. So one part of it is just kind of rotating about the pin, and the other thing that now we're thinking of is that it's flexing also. So it's the two pieces to it. And I know it's confusing because, yes, we did include that when we calculated the tilt, you know, about the pin, and so that would just be this far. But this part of the beam is not straight. It's tilted and flexed. So it's both of those added together. E is probably similar. Yes, E is the same thing. So once you find the slope at C, you do the same thing where, you know, it starts out at some angle, and then we actually did one like this. We did, oh, not a new section. Hold on. It was one of the really early ones. This right here. So this was, I don't know what class this was, but it was on Thursday, July 18th. So if you go back to July 18th, then we did, well, now it's not loading on me. We did this part where we found a slope, and then there was a point load on a cantilever beam. We took the slope section because we figured out how much it was sloped, which is part D in this problem, I think. And then that point load continues to deflect it, and so we have to add. Now I've exaggerated all these drawings here, so it does look like we're adding where they're not even supposed to be added together. Like we're adding that distance plus that distance. They're not even in the same direction. But you have to remember, I'm drawing them really exaggerated, and yes, they're not exactly in the same direction, but since they're really small deflections, they're essentially in the same direction. So you have to add this which is the arc length. Can't get it to spell what I want. Arc length. And we have to add this, which is the flex part, where it's actually flexing, bending. So that's how those work. It's kind of confusing. Will there be one with this kind of stuff on the exam 3? Probably not, but maybe on the exam 2 retake. Even this is a little bit much for a exam though, because it's so many steps of little tedious stuff that it kind of takes up too long, and I can't ask you many other questions then. Yes, I know it's confusing because I remember solving that problem, and the first time I solved it, I didn't include the blue section wherever it went. I've lost it now. That's the test review. I guess it was this pink section with the blue distributed load. I didn't include that to calculate that slope, but it does need to be there to calculate the slope. But the slope doesn't talk about deflection. It's just what angle is this thing at some point. And then from that point, because, well, I guess maybe if you think about it this way, you know, the slope at any point doesn't actually tell me how much it's deflected, and that only tells me, like, if it continued in that direction, I could calculate a deflection from there. But the beam is constantly flexing and bending, and so it doesn't continue in any particular direction at all. This slope is constantly changing. And so that's why maybe it makes enough sense that I calculate the slope at one point to see which way it started heading, but then it keeps bending based on the equation of the elastic curve that I'm going to use, or the deflection equation. Yeah, these are definitely beyond a test question, but just because they take too long to ask, I'd either have to make them weighted so heavily that they're a significant part of the exam, or you just wouldn't have, or make the exam really long. I guess it's already 2 hours, so that's pretty long. All right. Hopefully that at least helps you start to figure out if you ever need to do some more of this kind of stuff, this level of stuff. Then maybe it gives you some starting points. We'll be back Wednesday at noon with something much, much more straightforward than this particular thing. Get your teams formed. Don't wait on that, because there's not that much time